Hi everyone. In this video, we are going to pull all this information together that we now know about intermolecular forces and see how we can use it to predict boiling points for compounds. And when I say predict boiling points, I mean relative to other compounds given. So we'll be comparing the structural features of a series of compounds and then asked to predict, say, a ranking in order of low to high in terms of their boiling points. Remember that experimentally, if we measure the boiling point, we know exactly what to say about the intermolecular forces. The higher the boiling point, the stronger the total intermolecular forces. And all of those intermolecular forces are additive. So if we have London dispersion forces, which we do in all examples of collections of molecules, we might also have dipole-dipole, we could also have hydrogen bonding. And so those three present intermolecular forces are all additive. And whichever one is the strongest within the mix is kind of dependent on the size of the molecule. The larger the molecule, the more significant the London dispersion forces are. If we're talking about something small like water, then hydrogen bonding is the strongest because the surface area is just not there to have high contribution from the London dispersion force. So the first criteria we need to look at when comparing a series of compounds, and I'm going to just look at different pairs of compounds here. So when we're comparing two compounds in terms of what we might predict for their boiling point, we want to first consider the size. Okay, that is the most important thing. If my molecules differ by, my approximation is more than 30 molecular weight units, so more than 30 grams per mole, we're going to have the size take over here. And the London dispersion forces will be stronger, and therefore that compound that weighs more is going to have a higher boiling point. So looking at the difference between butane and hexane here, we have 4 carbons, so this is C4H10 versus C6H14. So we have 2 more carbons and a couple more hydrogens, so that's going to be a difference of about 30, right? So 12 plus 12 is 24, plus 4 additional hydrogens is going to give me 28. And in fact, here we see the boiling point for butane is 0 degrees Celsius and 68 degrees Celsius for hexane. And this is going to be the case for hydrocarbons, right? When we have all the same kind of structural features, size is really the only differentiating factor that we have to go off because these are both nonpolar. The only kind of intermolecular force that will be present here is the London dispersion force, which is dependent only on the size of the molecules. Okay? If we look at something like iodobutane versus butanol, okay? These compounds have very similar structures. 4 carbons, and here we have an iodide. 4 carbons, here we have an OH. So they look similar in their size. But if we calculate the molecular weight, iodine weighs a lot more than OH. So the molecular weight is going to be much higher here. We know that the heavier the atoms are, the larger they are. So there's more surface area, which leads to more London dispersion forces. So here we have the example where we have 2 molecules. One has a significantly higher molecular weight. So overall, the total intermolecular forces will be higher. We would predict then that this would have the highest boiling point. If we look at the experimental data, the boiling point is 130 degrees Celsius versus 118 degrees Celsius for butanol. So despite the fact that butanol can hydrogen bond, which is one of the strongest intermolecular forces, and it has dipole-dipole interactions, and it has London dispersion forces, the London dispersion forces in iodobutane are overall larger than the sum total of forces in butanol, just simply because the surface area contacts are going to be so much greater because iodine is so much larger. Now in this series of compounds, as we approach ranking these, we're going to start with considering the size. The size of these examples are all within a couple molecular weight units of each other, right? So oxygen weighs about 4 more than carbon, so this weighs 4 more than propane, and here we have 2 fewer hydrogens than we do here. So these are all plus or minus 4 molecular weight units from each other. So that is too close to make a call based on size. We need another criteria to consider. So then we look at polarity and hydrogen bonding. So the London dispersion forces are all going to be approximately equal here because the atoms are similar in size and molecular weight. We know that dipole-dipole interactions are stronger than London dispersion forces. So any molecule like acetaldehyde here or ethanol would be able to participate in dipole-dipole interactions because we have polar bonds and overall polar molecules. And then considering hydrogen bonding, we look for donors and acceptors. The only one here that has both is ethanol. So the fact that ethanol can hydrogen bond and has a dipole-dipole and London dispersion force compared to acetaldehyde, which has dipole-dipole and London dispersion forces, compared to propane, which has only London dispersion forces, we can break the tie here by looking at the overall strength of these intermolecular forces. The LDF, dipole-dipole, and hydrogen bonding total strength is going to allow me to predict that ethanol has a higher boiling point than acetaldehyde, than propane. And if we look at the experimental data, minus 42 degrees Celsius, 20 degrees Celsius, and 78 degrees Celsius. So what I would predict matches with the experimental data. In the last pair of compounds I have here to compare, we're going to need a third criteria. These have the same exact molecular weight, so we're tied in terms of the size. Moving on to polarity and hydrogen bonding. These are both polar molecules. They both have hydrogen bond donors and acceptors, so we can't break the tie there either. The third thing we need to look at is the surface area. What is the shape of these molecules, and how will they be able to stack against one another and maximize the surface area contacts? So the greater the surface area, the larger the intermolecular force. So imagine this interacting with other like molecules of itself, right? We maximize the surface area interactions here. Whereas this guy is more spherical, so when it is oriented with other molecules of itself, we have much smaller surface area contact, so a weaker intermolecular force here. So surface area becomes our final tiebreaker for this comparison. The boiling point is 97 degrees for propanol, 1-propanol, and then for 2-propanol, it is 82 degrees Celsius. Let's practice using these criteria to rank the compounds on the following slide according to their boiling point. So to first try ranking these compounds, we need to look at the size. Okay? The molecular weights, just by inspection, they all have 5 atoms. The atoms are carbon and oxygen. The first thing we need to look at when we are breaking this down is to consider the size. And these all have 5 atoms, carbon and oxygen, plus some number of hydrogens, which is kind of irrelevant. But looking at those atoms, they differ by just 4 molecular weight units. So just basically speaking, so the first thing that we need to do in order to break this down is consider the size of these compounds. These all, just by a quick inspection, have 5 atoms of similar molecular weight, so carbon and oxygen. Of course, there are some number of hydrogens that are not shown, but those are not going to have a huge impact on the overall total mass. So just looking at the chain of carbons and the number of types of heteroatoms there is sufficient. So these all have 5 large atoms, and they differ only by a couple units in molecular weight. So these will all be within that kind of 30 molecular weight unit guideline that I have set in place. So we need to move on. We need to consider the polarity. So we look for polar bonds. Those that have polar bonds will have dipole moments and therefore will participate in dipole-dipole interactions. So this will have dipole-dipole, as will the last example here. We need to then say, well, okay, these are tied in terms of the intermolecular force. Well, what other forces could be present? Well, maybe hydrogen bonding. So we look for hydrogen bond donors. There are none here, but we do have a donor here. So H bonding is possible here. Of course, all of these structures will participate in London dispersion forces, and they will be approximately equal because the size is equal. So my tiebreaker here comes down to the fact that this guy down here, propanoic acid, can participate in hydrogen bonding. And so this will have the highest boiling point, as we predict. This would have the second highest, and this would have the lowest. So if we look at the actual literature values, this has a boiling point of 36 degrees Celsius. The boiling point here is 80 degrees Celsius, and the boiling point here is 141 degrees Celsius. So we're able to use the criteria, size, then polarity and hydrogen bonding to figure this out. And if we needed to, we could go on and consider the surface area for a certain molecule. So if you have questions while you're solving problems related to predicting boiling points and the trends that go along with that, please reach out and let me know. Thank you for watching.